Okay, in this example, I have this 30 kilogram wheel, and it's unbalanced. So this red color is the weighted side of the wheel. And what I'm doing is I'm releasing this from rest, and I want to figure out what my angular acceleration and my acceleration of my center of mass is. And what I'm giving is my radius of gyration is equal to 0.15 meters, and I'm given some information about how far away my center of mass is from the center of my disk and the radius of this disk. So like always, the first thing we want to do, we want to draw a free body diagram. If we draw a free body diagram, we know that we have a center of mass right here. This is point G. And we're going to have our weight that goes right through our center of mass. So our weight is going to be equal to this 30 kilograms times gravity, which is 9.81. And we also know we're going to have a normal force because this is on the ground, it's rolling. We're going to have a normal force which acts perpendicular at the point of contact. So here's the ground, and it acts straight up in the it acts up in the y direction. And finally, we're going to have a frictional force, and our frictional force is going to act towards the left. Now, you might think this is weird, but this cylinder is rolling. So because it's rolling at this point of contact right here, its velocity is completely pointing towards the right, and that's where its motion is. So this point right here, this point is moving completely towards the right. So since our frictional force opposes motion, it's going to act opposite of this force right here. So our force is coming this way. Our frictional force says, no, I'm going to act against you, and I'm going to act to the left. So this is our free body diagram. And now we just have to draw a kinetic diagram. And with our kinetic diagram, we want to identify all the accelerations. So if here's point G, our center of mass, and this is what we're interested in figuring out, we know it's going to rotate like this. So this is going to be our moment of inertia about our center of mass times our angular acceleration. And because our center of mass is not the center of this this wheel, it's going to have two components of acceleration. It's going to have a component that's in the x direction right here, and it's going to have a component that's in the y direction right here. And this is equal to its mass times its acceleration. So 30 times the acceleration of y. And here, 30 times the acceleration of x. Try to make that a little neater. And it has these two components because it's not just moving in a straight line, like it's the actual center of the disk is doing. The actual center of this disk is moving in the horizontal direction only, and right now we'll just call this the acceleration of point O. Okay, so now we've identified our accelerations, we've identified our forces, and for convenience, let's just put our positive notation. This is going to be my positive x notation. This is going to be my positive y direction. And this is going to be my positive moment direction, and alpha direction. And all these agree with each other. Nothing is conflicting. So now I want to sum my forces in my x direction. And this is going to be equal to a mass times an acceleration of my center of mass in my x direction. And this is the positive way. So right here I'm going to have a frictional force F, which is equal to my mass times my acceleration in my x direction. I'm going to look at the sum of the forces in the y direction, which is downward positive. And this is going to be equal to a positive weight, so that's going to be 294.3 minus my normal force. This is a minus because down is positive and this is pointing up, and this is equal to my mass 30 times my acceleration in my y direction. And finally, I'm going to sum my moments about some point. I'm just going to choose my center of mass. There's other points you could sum this moment about. You could sum it about point A, you could sum it about the center, but I'm just going to choose the center of mass. And this is equal to my moment of inertia about my center of mass times my angular acceleration. Now, if you don't choose to use the center of mass, your moment of inertia is going to have to be modified somehow with the parallel axis theorem to accurately change the point you're taking your moments about. So if you took the moments about point A right here, I'm not sure if you really want to, but if you did, then your normal force and frictional force would cancel out, but your moment of inertia right here would have to be the moment of inertia about point A and not point G. So anyway, I'm going to do it about the center of mass right here, and when I do that, the moment of inertia about my center of mass, because I'm given a radius of gyration, my moment of inertia about my center of mass is going to be equal to my mass times this moment of inertia, or this radius of gyration squared, and it's going to be equal to 30 times 0.15 squared, or 0.675 kilogram meter squared. So again, this is my positive direction for my moments from this right here, and I'm taking about point G, so my weight goes through point G and does not have a moment on point G. Just the normal force and the frictional force do. So my normal force is going to want to rotate this way, and it's going to go the head of the vector first, so it's going to be positive. So we're going to have a normal force, NA, times the perpendicular distance, which is 0.1. And we're going to have a frictional force, which is going to want to rotate around it tail first, so it's going to be a minus frictional force times the perpendicular distance, which is 0.25. And this is equal to this 0.675 times alpha. And these are our three equations, but what's the problem? We have a lot of unknowns and we don't have enough equations for this. We have at least 1, 2, 3, 4, 5 unknowns. But we have to realize right here that this acceleration of x and this acceleration of y and this alpha, this angular acceleration, they can be related somehow. And they can be related by that fun equation, the relative acceleration equation. So with that, we have this acceleration of our center of mass is equal to the acceleration of this point O plus the angular acceleration crossed with the distance vector from G to O minus our angular velocity squared times our distance vector from G to O. Now, because this does not slip and no slipping occurs right here, we can say that our acceleration of point O, which is the center of the wheel, is equal to alpha times r. We know what our acceleration of g is. Our acceleration of g is going to have a y component plus some x component. And these are vector equations, so they need unit vectors. This needs a j component, this needs an I component. This right here, it's going to be, this is its magnitude, but it's moving in the positive x direction, so it's going to have a I component. And plus its angular acceleration. Its angular acceleration is going to be positive, so it has alpha times a k vector crossed with the position vector from g with respect to O. So this is from from O to G, because it's from G with respect to O, and we're going to go 0.1 meters in the positive direction. So this is going to be crossed with a 0.1, and because we start at rest, this angular velocity goes away. Now, we put in what we know. On this, we don't know what this alpha is, but we know this r. We know this is going to be 0.25 alpha in our I direction. We know a k, and this is also in I direction. We know a k crossing I is going to be a positive j, so right here we're going to have plus 0.1 alpha j. So if we separate our I and j components, we're going to have our acceleration of x is equal to 0.25 alpha. 0.25 alpha, and our acceleration of y is equal to 0.1 alpha. These are right here are j components, and this right here are my I components. So we know this acceleration of x is equal to 0.25 alpha, and my acceleration of y is equal to 0.1 alpha. So I can put this back into this equation right here, and I get my frictional force F is equal to 30 times 0.25 alpha. So this is equal to 7.5 alpha. And right here I can put my acceleration of my new expression for my acceleration of y into this. So I have 294.3 minus 30 times 0.1 alpha is equal to my normal force. What I did, I moved this to the other side of the equation, and I switched these two. So this becomes a minus and this becomes a plus. And this normal force right here is going to be equal to 294.3 minus 3 alpha. So now, what can I do? I have an expression for frictional force in terms of alpha. I have an expression for my normal force in terms of alpha. So I can put this into this equation right here, and I can put this frictional force into this equation right here for the frictional force. When I do that, I have an entire equation just in terms of my angular acceleration. So if I put this in, I get this is in terms of angular acceleration, this is in terms of angular acceleration, and of course this is in terms of my angular acceleration. So when I substitute this in and solve for my angular acceleration, I get my angular acceleration is equal to 10.34 radians per second squared. Now, with this, I can solve back from my normal force. I can put this right in here, and I can get a normal force which is equal to 283.96 newtons. I can put it back, this alpha, I can put it back into to solve for a frictional force right here, and I can get a frictional force which is equal to 77.55 newtons. And I can also use this equation right here, what my acceleration in my x direction is, what my acceleration in my y direction is, and I can get an acceleration of x, which is equal to 2.58 meters per second squared in this direction, and an acceleration of y, which is equal to 1.034 meters per second squared in this direction. I know the directions because of the positive signs on them. So this becomes what my acceleration of my x direction and my acceleration of my y direction is.